The next type of function that we're looking at actually is a very important function, the log function. Allows us to do all sorts of things. Let's just define them. Basically, it's the inverse of exponentials. So the inverse of raising to a power. If y is a to the power of x, so there's the exponential. It's the inverse, so therefore x is equal to log y. Because remember, when you apply the inverse, it undoes the inverse operation. So when you apply the log to y, it undoes, if you like, the exponential. So it no longer is base a, it just becomes x. So that's how we would, if we wanted to make x the subject, that's how we do it. We log both sides, basically. Log both sides. But notice the log also has a base. The base doesn't change. More importantly, we're going to be interested with base e. Base e. And so it becomes log base e, known as the natural logarithm. Sometimes for that reason it's written as ln rather than log. And you might notice on your calculator the ln button, which you might have thought said in, but it's actually ln. But that's what it stands for, because I think it's because of the French. You know how they all say their words backwards? Instead of saying natural logarithm, they go logarithm naturel. True, I think. But if you just see log with no base written, we assume they're talking about the natural log. Used to be, and I'm going back to the 1970s now, yes, I know I'm old. It used to be if there was no base, you would assume it was base 10, which is known as common logarithms. But that's all to do with the log tables we used to use back in those days before we were allowed to use calculators and what have you. So it was the common one we used. But these days, the natural logarithm, because we've all got our calculators and we can press the buttons nice and easily. The logarithm curve, well, we know what the basic exponential curve looks like. It's the same as the exponential curve, but now the x and the y have swapped over. So instead of going through 1 on the y-axis, all your basic log curves go through 1 on the x-axis. And instead of it being asymptotic to the x-axis, it's asymptotic to the y-axis, and so on. Now, of course, it depends on the base. Same with the exponential. If your base was bigger than 1, then the exponential curve flipped around the other side. And so we get the same here. If it's bigger than 1, it's the red curve. If it's in between 0 and 1, it would be the blue one. Now, E is around about 2.7. So the base E log curve would look like the red one. So its domain greater than 0 and range all real y. There's no breaks in the curve. So laws. Well, because they are tied in with indices, and this is what I was saying, is it allowed us to multiply big numbers together, because when we said, okay, let's work with the logs, I can add the logs together, and that's a lot easier. Adding two numbers together is a lot easier than multiplying two numbers together. And so log of m plus log of n is the log of m times n. And subtraction is division. Very similar, if you think about it, to the index laws. When you multiply two numbers together, you add them, and when you divide, you subtract them. Log of m to the power of n. This is the one that allows us to solve those equations, because now you can bring the power to the front. The n comes n log m. And just like we lie to you when we say anything to the power of 0 is 1, remember that lie? Well, it's the same with logs. We lie to you there too. Log of 1 is always equal to 0. That's another lie. Because of course, 0 to the power of 0 is not 1. Well, same deal here. If it was log base 0, it wouldn't be 0. It's another one of those ones which is just a weird number that we don't understand. Log a base a is equal to 1. Because basically when you read a log, you're saying the base to the power of what would give me this number. So log a base a, we're saying a to the power of what would give me a. Oh, a to the power of 1 would. So that's why it's the answer. They would cancel, because if the bases are the same, the exponential and the log cancels. So it's log base a, but a to the power of that, they cancel, and you just get x. Okay? If it was, say, 5 log x, you'd need to use your log laws to move the 5 inside the log, because it has to be a to the power of log. It can't be a to the power of something log. Right? So you'd have to play around with your index laws. This is what we call the change of base rule. I guess that's handy because our calculators only have base 10 and base e on it. So if you needed to work out a log of base, I don't know, 2 or 5 or what have you, it's not on your calculator, but you can change it. And it's really simple to do. You just basically change the base. I wanted log x base a, I'll change it to b. But you then divide it by the log of that old base in the new base. So it stays as log b. So if I wanted to find log base 2 of 8, answer should be 3. Let's prove it using our calculator. I've got a calculator handy. Is this one going to turn on? Yes, it is. So let's say I did it in base 10. I'd go log of 8 divided by log of the old base was 2. Hopefully the answer is going to be 3. 3. It worked. Woohoo! So you got this sort of question. Remember, what we're saying is the base is 5. 5 to the power of what would give me 125? And if you're really unsure, I suppose another way of solving this problem is you could say, let's undo the log. Well, to undo the log, exponentialize, if that is such a word, both sides. So the left-hand side now becomes 5 to the power of x. It undoes the log on the other side. So as I'm saying, 5 to the power of what is 125. 5 cubed is 125. So this one, x to the power of 3 gives me 343. So let's rewrite it that way. It makes it a little bit easier to solve. Cube root of 343, 7. Just a fancy way of doing the same question. Instead of saying x equals, it's just saying, hey, work out log 16 base 4. 4 to the power of what is 16? 2. Now, if you don't see it straight away, you could play with the log laws. You could say, well, 16 is 4 squared. Now, I can use my log law to bring the 2 out the front. Log 4 base 4. Remember, we had the rule that said log a base a was always equal to 1. So 2 is my answer. But as I say, the quicker way of doing that question is to simply go 4 to the power of what is 16? 4 squared. That would be 2. 6 to the power of 2 log 3 base 6. And this is what I was talking about. You need it to be to the power of log, not the power of 2 log. So I'm going to use my index laws to make that log of 3 squared. I'll bring the 2 inside the log. Now, the 6 to the power of log 6 will cancel. And so it's 3 squared. 9 is the answer. Log 2 base 16. No, sorry, I said that the wrong way around. Log 16 base 2. Log 8 base 2. Well, they are the same base. So I could use my log law and say, well, hang on, when I add logs, that's the same as multiplying. Or I could work these out individually and then add them together. Choice is, well, I was going to say endless, but I suppose it's not really endless. That's pretty much it, isn't it? Just one of those two. 16 eighths are 128. 2 to the power of what is 128? 2 to the power of 7 is 128. They're all base 10. Now, this is where it becomes a bit harder to do that because 10 to the power of what is 125? Well, hang on. That doesn't work out nice and neat. So I'm going to use my log laws. Adding, we multiply, so 125 times 32. Then that divided by 4. Phew, wasn't that nice? Worked out to be 1,000. 10 to the power of what's 1,000? 3. Oh, well, people get confused when they look at this one and think, oh no, I've got to change the base. But you don't, because if you look at it, it's already in the form of a change the base. So I could rewrite that as log 8 base 2. So just that change of base rule in reverse. And 2 to the power of what's 8? Well, 3. 3 is the answer. Square root of 1/8. Now we can't find the square root of 8, can we? So in that case, I'll make that 1/8 is a power of a half. Bring the half to the front. 2 to the power of something is 1/8. We can do that one, can't we? It's -3. -3. So a half of -3. -3 on 2. This is where they're really useful, of course, is solving exponential equations. Although this one does work out nicely because I can write 1 on 27 as 3 to the power of something. So this one I could go, oh, that's 3 to the power of -3. 2x plus 1 is -3, and we go and solve and get x equals -2. But they don't all work out that nice and neat. So 2 to the power of x is 9. Oh, hang on, how do we do that? So we log both sides. That means the x can come to the front, and there we get it. What essentially you're doing is changing the base, if you look at it. Because we're saying 2 to the power of x, the base was 2. Oh, I'm changing the base so I can work it out. So it's log 9 divided by log 2. So log of what I'm finding over the log of the old base. 3.17 roughly. Okay.